Hello students, so welcome back to our new video on solid state. Okay, so today in today's class we are going to discuss about the topic that you could see on the board, that is close packing in crystals. Okay, so already we have discussed about the crystals, so here we are going to discuss about their packing. Okay, in the arrangement of atoms or the ions that are present in the solid crystals. Okay, so as we are discussing about solid state, so first we have to start with the one dimensional arrangement. Okay, as we are going to start the arrangement of atoms, going to discuss the arrangement of atoms or particles, okay, or ions present in the solid state. So first we have to start along one dimension. So the first is close packing in one dimension. Okay, close packing along one dimension or in one dimension. So in one dimension means what? Just like along the x-axis, okay, or along the y-axis or along the z-axis. So here we are just discussing when the particles are arranged along the x-axis. Okay, so suppose here are some spherical particles which are arranged in a rigid structure, okay, in this way. So just we have to consider any particle. I am considering this particle. Okay, so in this way all the particles are present in a very congestive way and along the straight line or along in one direction. So what is the coordination number of this particle? So what is coordination number? Coordination number is the number of particles which are present and which are adjacent to this particle, which have a touch, okay, which are present and which have a physical touch with this particle. So what are the particles which are directly touching or which are very close to this particle? So as we could see, on both sides this particle is attached with these two particles, right? So what will be its coordination number? What is the coordination number of this particle, or what is the coordination number of any particle? Not only this, if you are taking any particle of them, then the coordination number will be same for all of them. So what is that? That is 2. Okay, because we could see that in this line or along this axis all the particles that are present, and it is directly connected with two particles that are present on both sides of it, right? Each and every particle is connected with the two particles that are adjacent to it, and that is connected on both sides of it. So according to this, the coordination number in one dimensional close packing, coordination number of any particle which is present in one dimensional close packing is 2. Okay, that is 2. So this is clear, I think. So next we are going to discuss when the close packing is in 2 dimension. Now close packing in 2 dimensional field. So in 2 dimensional field there could be 2 types of arrangement. There could be 2 types of arrangement. Okay, the first one is square close packing. In short, it is denoted as SCP. Okay, square close packing, in short SCP. So in the 2 dimensional field, the first type is square close packing and the second is hexagonal close packing. The second type is hexagonal close packing, which is denoted by HCP. Okay, which is denoted by HCP in short. So now we are going to see their structures. So what are their structures like? So as we know, two-dimensional means what? One-dimensional means just only in one direction, just only x-axis or only y-axis or only z-axis. But when we are going to discuss about two-dimensional structure or two-dimensional arrangement, so then we have to take two axes, okay, just like x and y-axis. So this is x-axis and this is y-axis, okay. Here also any two axes you could take xy, yz or xz, as because they are having angle 90 degree between them, okay. Two perpendicular axes we have to take. So this is the two-dimensional field now. Now what will be their arrangement? So always we have to start from the one-dimensional arrangement. So in one-dimensional arrangement, what we have seen, that the particles are arranged in this way along the x-axis, right? Here also same. The particles are arranged along the x-axis. Clear? Next. So in starting, both of them have started in the same way. So what is the difference? So in square close packing, the second line that is coming, okay, the second line that is coming or the second row that is coming, in that case, atoms will be just over the other atom. So in this way, this atom will be over this one, this will be over this one, this is over this one, this is also directly above this, okay. In the second line, the atoms that I have drawn here, that will be just directly above the atoms that I have taken in the first row, okay. This is the first row, this is the second row. In the third row again, just you have to draw them above the atoms that is present in the that is present in its lower row. That is the square close packing. Now in this case, what will be the difference? So here what we have drawn, we have just drawn the atom just above the atoms that are present in the lower row. But here the difference makes is, just you have to check the gap between these two atoms or between these two particles, and you have to draw the atom here above the gap, not above the atom, okay. There is a gap, there is a little gap between these two particles. On that gap, that particle will come. Here also that, here also. All will be the spherical shaped, okay, in this way. So on the gap that is present between two particles, on that gap, that atom will be present, okay. In this also, here also, this one, okay, by this way. Now again we have to consider their coordination number, okay. And one more thing, that is, this type of arrangement is called AA type. This type of arrangement is called AA type, and this type of arrangement is called AB type. Because here you could see that all the rows are identical. All the rows are identical and all of them are the type of A. Okay, but here all the rows are not identical. All the rows are not identical. So if it is the type of A, then that will be the type of B. Then it is the type of A. Now you could consider one thing. These two rows are identical because this atom, these two rows, okay, the first row and the third row, these two are identical. Just you can check this atom and this atom, they are directly above each other. Now these two atoms, they are directly above each other, these two atoms also. So that means these two, the first and the third row, they are identical, okay, but the second row is different, and that's why the second row is given the letter B, and the first and the third are given the letter A. But here all of them are identical, so these are denoted by A. Clear? Next thing, now here we have to calculate their coordination number. So just take any one particle, okay. Now what we have to check, that with how many particles this particle is directly connected. So just see here, with this it is directly connected, with this also, with this one, and with this one. So with how many particles it is directly connected? Tell. This is the first, this is the second, this is the third, and this is the fourth. That means here the coordination number is 4. Okay, here the coordination number is 4, and if we could connect their centers, then what type of structure we are getting? We are getting a square, right? We are getting a square type structure here, okay? So that's why it is called square close packing. Now come to this structure. So here suppose I have taken this particle, okay, and just again we have to check that with how many particles it is directly connected. So you could see here, with this one, with this one, and with this one. So how many atoms or how many particles are present adjacent to it? That are 6. So the coordination number is here 6, and if we could join their centers or these lines, then what type of structure we are getting? We are getting a hexagon. Right? We are getting a hexagon. Here we are getting a square type structure. So as we are getting a hexagonal type structure here, so from there the name is given as hexagonal close packing. And as the type of structure is square here, so that's why it is named as square close packing. Clear? So that is the concept. Now what is their packing efficiency? What is their packing efficiency and what is the percentage of void? So I am just removing this upper part. Okay, so now if we could see this one, so what is the type of void here? So now here you could see that the void means what? Void means the space or the gap that has been produced between the particles. As all of these particles are spherical in shape, so they could not occupy the total volume, right? They could not occupy the total volume. So obviously there should be some vacant space between them, and this vacant space is called void. Now just observe its structure carefully. Could you observe the structure? The structure is like again a square, right? The structure is again like a square. So this is the structure. It is having a quadrilateral shape. The void, it is having a, not actually square, quadrilateral shape. Okay, Now come to this part. So here we could see that this is the minimum amount of particles you have to take which could make one void. Okay. So here we require 4 particles to make one void, and here 3 particles are sufficient enough to make one void. So now just see again here, this void that we are getting from the hexagonal shape, that is having the structure like triangle. So this void is triangular shaped. This void is triangular shaped. Okay. So now tell, between quadrilateral or between a square and between a triangle, which one is having maximum volume or which one is having maximum area or maximum space? The answer is quadrilateral. Okay. The space, if you could compare them, then the space occupied by the quadrilateral is higher than the space occupied by the triangle. So here the space of void is high. The space of this void is high, and here the space of this void is void is low. Okay. So these things you could copy in your rough copy or in your fair copy also if you want to do. Otherwise everything is written in your notes, PDF notes. Okay. But this thing that I am telling, so this here the space of void is high for it and the space of void is low for it. Now come to one conclusion from here, where the packing efficiency is high. Packing efficiency means what? The volume that is occupied by the particles. So where the packing efficiency is high, so there the void will be low, right? Where the packing efficiency or the volume occupied by the particles is high, so there this vacuum or there this void will be low, and where the packing efficiency is low, there this vacuum will be high. Just a relation between packing efficiency and the void, that is reciprocal. Packing efficiency is inversely proportional to the space of void. Okay. So in between this it has higher space of void. So for this the packing efficiency will be low. In short I am telling is P dot E dot. So here the packing efficiency is low, and what is the value of packing efficiency here? That is 52.4%. Okay. And here the packing efficiency will be high. And what is the value of packing efficiency here? The value of packing efficiency here is 60.4%. So from here short questions could come that between the square close packing, between the square close packing and hexagonal close packing in 2-dimensional structure, which is having higher packing efficiency, which is having lower packing efficiency, or which is having higher space of void, or which is having lower space of void. So I think this is clear for you all. So next I am moving to 3-dimensional arrangement in crystals. Next is 3-dimensional arrangement. Okay. So again we can classify it into 2 types. The first one is again square close packing, or SCP. Another one is again hexagonal close packing. Because the packing will not change, the type of or the nature of packing will not be changed. Okay, 3-dimensional means what? Now not only x and y axis as well as a z axis is also there, right? Not only x and y axis, along with this a z axis is also there. That means just like a box or just like your room, okay, it has length, breadth as well as it is having a height. So now the packing could be this type, two types. So what is the square close packing? So again here, suppose this is a box. Okay, this is a box. So here these are the particles. Here also it will be. In this type. Okay. So here if we could see that what will be the coordination number. So here the important question is about coordination number, because in short questions it could be asked that what is the coordination number in square close packing for 3-dimensional area. So that you have to notice. So what will be the what will be the coordination number for here? If you could see, then you could see that each and every atom, it is connected with 6 atoms in its front side and in its back side, in upper region, in lower region, okay, and in the right side and in the left side. So in each and every case you could see here 6 directions. On 6 directions it is sharing its atoms, okay, it is sharing its atoms in its 6 directions or along the 6 directions. So therefore in square close packing the coordination number is 6. Okay, in square close packing the coordination number is 6, and just that part I have mentioned here. Just all the atoms are just above the its previous row or upper row. All the atoms are just present just below or just above the particles or atoms. Okay, so that's why it is square close packing. The square close packing type of structure is also mentioned here, but here the coordination number, if you want to see, then you could see that suppose this is one atom, it is connected with this one. Here also in its front there will be, okay. So just like in each and every direction, okay, in this way, in along x-axis, just think about x-axis. Along x-axis we could get a positive direction, a negative direction. In mathematics you have done. Along x-axis in positive direction, in negative direction. Along y-axis in positive direction and in negative direction, and along z-axis also in positive direction and in negative direction. So how many sides are there totally? 6 sides. So 6 directions. So along 6 directions it is directly connected with 6 particles. So that's why it is having the coordination number as 6. Okay. Next is that hexagonal close packing. In hexagonal close packing, so just like this one, suppose these are the 6 particles that are present on 6 sides, because it is having a hexagonal structure. So just I am showing the basic part. Okay, this is the hexagonal part. Now what will happen? Just now you have to look it carefully. For that, drawing of the proper diagram is very important. Okay. Now see how many voids are being formed here. How many voids we are getting here? We are getting here 6 voids. This is the first. This is the second void. Void means the gap between the particles. This is the third void. This is the fourth void. This is the fifth void. And this is the sixth void. Right? 1, 2, 3, 4, 5 and 6. Okay. So there are totally 6 voids or 6 gaps present between these particles. Now what will happen? This is the layer. Okay, and another thing, that is, this is again known as AA type. AAA type, because all the rows are identical. Okay, all the, not actually row here, all the planes, XY plane, just like XY plane, all the planes are identical here. But here those planes will be of ABAB type. Hexagonal close packing has two types. One is ABAB type, another one is ABC type. So first I am discussing about ABAB type. Now see, so that is clear that these are the voids 1, 2, 3, 4, 5, 6, clear. Next, in the next layer, okay, in the next layer, the particles that will be coming, okay, that will just sit above the void. Okay, suppose this is a particle, this particle I could place above the void, above the first void. Okay, the first void. Now the second particle that I will not place here, that I will place on 3, on alternate voids. Okay, second particle done. Now third particle that I have taken, that I will put on the next alternate void, that is 5. So that means in the upper layer, on which voids I am placing the particles? I am placing the particles on the alternate voids, which are 1, 3 and 5. Okay, which are 1, 3 and 5. So just imagine, here is one particle, here is one particle, and here is one particle. That is done. So if we consider this layer that I have drawn here, okay, that hexagonal layer, if you consider it as A, then the particles that I have told, just like this one, I am just removing the upper part. These are all imaginary type. Just you have to increase your level of imagination. Okay, this is the one. So in the above layer, the particles will be like this. I'm just not showing this. Just these particles. Okay, this is one. This particle is above the void 1. This particle is above the void 3, and this particle is above the void 5. Clear? So if this is the A layer, so now this is the B layer. Okay, if this is the A layer, this is the B layer. Now that is above. B layer is just above the A layer. Okay. Now next I am putting the third layer just below the A. I am putting the third layer just below the A. So where I will put the next particles, again I will put the next particles, okay, just below 1, just like these 3 particles above this B level is there. Now if this is the layer, now below this again I am putting particles on 1, particles on 3 void, and particles on the 5th void. Okay, so just I am missing these 3 voids, 2, 4 and 6. These are remaining vacant. Okay, these 2, 4 and 6, these voids are remaining vacant, and again I am placing the particles below the layer A, and on below which voids I am placing it? Below the void 1, again below the void 3, and again below the void 5. So these particles are remaining vacant here also. So that is also the same type, that is B. This is also looking like a upper triangle, and this is also looking like a upper triangle. Okay, and this is looking like a hexagon. So that is the structure of hexagonal close packing in ABAB type. Okay. Now what is the coordination number? So here you could see what is the coordination number of this particle. In this layer, in the A layer, the coordination number is 6, right? 1, 2, 3, 4, 5, 6. 6 particles are there. In the above layer, how many particles are connected directly with it? That is 3. And here in this particle, in this layer, this particle is directly connected with this 3. So here also 3. So what is the total coordination number? That is 6 in the layer A. 3 in the above layer, and again 3 in the below layer. So total coordination number is 12 for this. Okay, this is AB type. Now another type is there that I have just told, that is ABC type. So what is the difference between AB type and ABC type? What is their difference? So now what will happen? So in the below layer, what we have done in the first case, we have put the atoms just again below 1, 3 and 5. But in the ABC type, what we will do? We will choose the alternate voids. Okay, so not 1, 3 and 5 again. So we are choosing this one, 2, 4 and 6. These alternate voids we are choosing here to place the particles. So here the triangle will be looking like a inverted triangle. Okay, inverted triangle. So what will happen? This is the middle layer A. In the upper layer we are placing the particles above the void 1, here 1, okay, here and here 1, 3 and 5. And in the below region, in the below layer of A, we are placing the particles where? In alternate angles, in alternate voids. That means in 2, in 4 and in 6, which were kept vacant during AB. Okay, so that is the basic difference. So here we are getting to inverted triangles, and in the middle a hexagon. So that's why it is called ABC. So what will be the coordination number here? The coordination number will not change. That is the same, just like this one, because in this layer it is connected with 6 particles, in the above it is connected with 3 particles, and in the below it is connected with this 3 particles. So here the coordination number will be same, that is 12. Okay, so these are the close packing of the crystals. So in our next class we will discuss with the next part of this chapter, and if you have any query regarding this, we will discuss it in our live classes. Thank you everyone for watching this video.